Hello, everyone. My name is Rahul Malik, and I'm an iOS engineer at Pinterest. I work on the core experience team where we work on building tools, frameworks, and general abstractions to help developers move faster every day. I've gotten the question a bunch of times yesterday about what the scale of Pinterest is these days when it comes to iOS. So I thought I'd bring a few numbers up for you. Currently, we have about 50 iOS engineers working across a variety of teams. These engineers have contributed, including external dependencies, about 690,000 lines of code in our code base. And a more fun statistic that I've found recently is a commit lands every 7 minutes on average in our code base. So a problem that we think a lot about, and a problem that I think is not general to Pinterest, is how can we continue to move fast with quality? How can we enable, as we add more engineers, how can we enable them to continue increased velocity while keeping the product quality high? You can add static analysis, you can add unit tests, but really what would be ideal is if the environment we developed in was preventing us from making mistakes. If the environment we actually worked within would reduce our risk while allowing us to move fast. And the environment, in my opinion, is domain-specific languages. This is a cat that moves fast. Probably with questionable quality, though. Now, throughout the course of this talk, we're going to talk about writing domain-specific languages in Swift. And when we talk about domain-specific languages, Martin Fowler described them, if you're not familiar with them, as a computer programming language with limited expressiveness focused on a particular domain. Now, the limited expressiveness is the power of a domain-specific language. Because it doesn't have to solve every problem, it's good at solving very specific ones. So if you've ever used a makefile, you've used a DSL before. It's basically a DSL for writing shell commands. A pod file is a DSL for expressing third-party dependencies through CocoaPods. And QuickCheck or SwiftCheck is a DSL for property-based testing. So, but before you start to change how you write your code, you should always ask, why? Why should we do this? And there's a few reasons I like to point to. First one is DSLs are easy to use. When you write a DSL, the fact that it's limited expressiveness makes it easy for people to pick up. It's generally you can look at other examples of how this DSL was used and start coding right away. Second is safety. Because you have the limited expressiveness, you're able to actually constrain your APIs and use the type system to promote safety throughout your code base. And last but not least, it's declarative. Users that are using your DSL are basically declaring what they want to do, and they rely on the DSL to translate that intent into action. And we're going to see this theme come up throughout the course of this talk. Now, not all languages are great for writing DSLs. This is from a guy, if you recognize his handle, Codify. He wrote, C is basically a domain-specific language for writing unsafe code. Yes, it is. And the idea behind this statement is that not all languages are actually suited to writing domain-specific languages. There are certain characteristics you want to look for. So functional languages, sort of on the other side from C, have a lot of the characteristics that we're looking for. You want a strong type system because you need that to actually properly model your problem statement. You want features like higher order functions and lazy evaluation so you can build modular and composable abstractions. And you want a language that doesn't promote a lot of boilerplate syntax so that you can feel like you're actually developing in a new language. And while I'm not here to have the debate about Swift being or not being a functional language, it has these characteristics, which is what's important. Now, when I've created DSLs at Pinterest, I followed a few basic steps. One, we got to model the problem. So this requires you thinking kind of abstract about what you're trying to do, and then using the type system to actually define it. Second, you want to focus on building modular and composable abstractions that take your model and actually turn that intent into action. And then last but not least, work iteratively. Sometimes you might try to model a problem that's very big, and it might require multiple DSLs to actually accomplish. Now, to sort of illustrate how we use this recipe, I'm going to go through a couple examples at Pinterest. The first one is a project we called PinCore. Now, if you were here for Pedro's talk yesterday about microfeatures, it's a very similar concept. Essentially, we had one giant monolithic application that we were trying to break up into a set of core frameworks. And when you looked at any of these frameworks, we wanted you to be able to have some level of consistency in terms of how they were laid out, so that the file hierarchy, no matter if you were familiar with that framework or not, you would know where to look for sources and tests and general configuration. So we took inspiration from the Swift Package Manager. If you've used the Swift Package Manager, you might be familiar with this command, Swift Package init. What it does is, if you enter a directory like my library, you can use Swift Package init to bootstrap all the necessary files and directories to actually create a new package. So in this instance, you see that we have a library called my library. There's a package.swift file that declares our package, and we have a sources and test directory, and then inside that test directory we have another directory, and then we have a few Swift files that allow us to get a module that compiles and one sample unit test. Now, if we were to start writing a Swift script to sort of accomplish this, it might look like something like this. You know, we say what our framework name is, we create the directory, we hop into that directory, then once we're in that directory, we create the next level directories, we add git keep files, and then we go in the test directory, we make another one, and then once we've created all directories, we start to actually add files to those paths, and you know, you get this working, you run it once, and it does what you want to do. And you're like, hooray, this is fine, we can ship this. This is exactly what we intended to do. But there's a lot of problems with this. And the real things you'd want to look out for here is it's actually quite error prone. If someone that wasn't familiar with the script didn't actually know what it was supposed to do, they might say, try to add a file before we created directories. You could have had issues where you've evaluated the template, but you specified an incorrect, like an incorrect template path. And the second part is that it's hard to follow. When you look at this script, it's not obvious what we're trying to accomplish here. It's not obvious what the final directory structure is supposed to be. And last but not least, it's imperative. The user is required to remember what directory they're in. They have to hop in and out. They have to evaluate templates. They have to do a lot of work that they shouldn't have to do, that should just be sort of done for them. And so the first step to sort of fix this with domain-specific languages is let's figure out how to model the problem. Now, when we're thinking about modeling problems, we're really thinking about how to use the type system correctly here. And one sort of very useful part of Swift is enums, and more specifically, recursive enums. If you're familiar with Swift enums, you can actually represent different types effectively through multiple case statements. It's unlike other enums in Objective-C, where everything is just an integer or a single type. And then if you add the indirect keyword to a particular case, it can reference its parent type. So in this case, node's left and right attribute can reference tree. And this is powerful because now when you actually create an instance of this tree enum, it can be infinitely deep. It can be a recursive data structure. And when a type actually forms, and when a type actually represents multiple types, it's also known as an algebraic data type. And algebraic data types are really useful in the functional community for modeling problems. Now, if we go back to what we were trying to do by creating directories and files, we can actually create a directory item enum now. And the first case would just be file, which has a name that's a string, and contents, which is also a string. And then we have an indirect case, or recursive case, that's folder. And it just takes the name of the folder, and then its contents is an array of directory items. So that means that folder can contain any combination of files and folders underneath it. Now, we can actually create an instance of this enum that sort of declares what our package should look like. We can say that the outer folder is called my library, and then inside of it there's a git ignore, and then there's a sources and test directory, a directory underneath that, and you can sort of see where you can see visually where everything is supposed to go. You can see what files belong in what folders. And then we can take that model and we can actually then write simple functions that transform that intent into action. So in this instance, create files will take an instance of directory item, and then it'll switch over it. If it's a file, it'll write that file to a specific path. And then if it's a folder, it'll create that folder, and then it'll go inside of it, and then map over its contents and recursively create files. And then it'll hop back out. And now this is just a simple 10-line function, but it's actually really important here because this isn't specific to the exact file structure we were trying to create. It's a very general testable function. It's something that you can look at and easily reason about. But you don't have to stop there. Now that you have a data structure that expresses your intent, you can actually write other functions. Like, let's say I wanted to have this script have a feature where we just print out all the files. We don't actually create any directories or create any files. So you might write a function like ls here that sort of models the command line operation. So, but what we've done here is we've created a deeply embedded DSL. A deeply embedded DSL is one where the computation results in a sort of complex representation, or a data structure, if you will. So to sort of illustrate that example, 1 plus 2 is equal to the expression of the sum operator and 1, 2. Deeply embedded DSLs are actually really important and really powerful, and the reason is that that complex representation can be optimized, transformed, and into whatever form you need. So you can think of a lot of examples where if you create a deeply embedded DSL, you can actually do further optimizations and transformations on it. The second example I want to talk about with DSLs at Pinterest is a project we open sourced recently this year called Plank. Plank is a code generation tool that generates immutable models from JSON schemas. So I thought code generation would be an interesting topic for us to talk about with DSLs. Now, you can think of code generation at a very high level as it's basically some function that returns an array of strings, where each index in that array is a different line in a file. So if we were trying to generate, say, the body of the Fibonacci function, we might start with something like this. And this might be sort of like the first MVP attempt, and technically it works, but it has a lot of problems. You notice that there's issues with syntax here. We could have easily forgotten a brace. There's no safety here. We're saying explicitly how if and else statements should be rendered. We're implicitly saying what the style attributes of this code generator is. We don't have, like, if we wanted to add a feature later where people could specify, say, the indent level or where the braces are, this would be hard to model later. And it would be hard, and especially if we add more and more methods that are built the same way, it would be hard to fix at a later time. So let's think about how we can model this. Now, everyone understands this, I'm pretty sure, but an if statement is just some condition followed by an execution block, and then an else statement is an execution block that follows an if statement or an else if statement. So we talked about enums last time, but now we're going to talk about functions. So we could create a simple function called if statement that takes a string that's a condition and a body that's a code generator. And if you remember from the first slide in this section, code generator is just an anonymous function that returns an array of strings. Now, so simply all this function does is template out if some condition and embraces, and then the execution body. And then the else statement is very similar. It just doesn't have the condition. But since these are sort of small building blocks, we can take them to compose more like interesting functions like if else. And so if else is a little bit more complex, but I'll sort of walk through it. It's a function that takes the if statement condition and body, but it returns a function that takes a code generator as an argument. And so what that means is that the result of the if-else statement is a function that takes an argument, which in turn takes the else block. So this is probably clear with an example if you look at this. So this is Fibonacci written with the if-else statement DSL here. So we're able to now actually look at this and understand what it's supposed to do. I'm not worried about if we've missed a brace or not. I'm not worried about if we're implicitly saying what the style of this code generation should be. And it's actually quite expressive. I can read it almost like I would just read regular code. And so this wouldn't really be possible without higher order functions. And higher order functions allow you to pass and return functions as arguments. So they allow you to build composable and modular abstractions. And higher order functions are really valuable when you're creating shallow DSLs. Shallow DSLs are like a fixed representation of computation. So if 1 plus 2 equals 3, that's an example of a shallow DSL. And in turn, what we did with code generation is we had functions that evaluated to an array of strings. We didn't know if the code we actually looked at the end was generated by the if statement function followed by the else statement, or if it was created by if else. So our code generation like process here was actually creating a shallow DSL, as contrasted with our file hierarchy DSL, which was a deep DSL. Now, I want to talk about things that we haven't done at Pinterest also. So I thought it'd be fun for us to kind of build something new, something that's more general to everyone. And so the topic I want to talk about today is GraphQL. Now, how many people here have worked or read up on GraphQL before? Okay, it's kind of dark. I'm assuming that's half the room or more. So, but if you're not familiar, GraphQL is a query language for APIs. It's an alternative to RESTful endpoints, which means that instead of having different API endpoints you query for different sets of data, you actually just have a single endpoint that you request all your data from. And that one endpoint knows how to fetch all that data from your backend. So for this example, I wanted to pick an instance that would be familiar to everyone. So GitHub actually released a version of a GraphQL API not too long ago. It's in alpha right now. I encourage you to check it out. But at least it will give us a schema that I think everyone's a little bit familiar with. So if you've never seen a GraphQL query before, it looks something like this. So issues in a repository, that's our example here. So in this case, I want to see for the Pinterest Plank repository, what are the name, description, homepage URL? So you can see that like the repository takes some arguments and some fields, and then we might have a requirement change where in our feature we want to also display the avatar URL of the owner, and then we also want to get the user or get the issues. So we're going to say, give me the first 10 issues, and for each one of those issues, give me the title and the state. And when you execute this query in GraphQL, you get a response that's in the shape of your actual query. It actually matches what you've requested, which is great because it makes it really easy to understand what the response will be, and it makes it easy to sort of derive parsers and general logic on that. So, but GraphQL is an example of an external DSL. An external DSL is one that it's basically a standalone language. It has its own tools, it has its own interpreter, it has its own grammar and syntax, whereas what we've been talking about this whole time, which is internal or embedded DSLs. Now, internal or embedded DSLs are ones that are written and run within the host language. So in this case, we're writing DSLs in Swift that run within the Swift runtime. So the problem we have is if we want to continue down this route of creating internal embedded DSLs, how do we actually bring GraphQL into Swift if it's an external DSL? How do we actually write concise and type-safe queries? How do we move fast with quality here? Now, a first attempt might look something like this. So if you gave this to someone and they just needed to get the job done, they would run this query against GraphQL. They would say, okay, I tested it once, it works. And then I created an array of strings, and then I joined them, and then I just sent that off. And then if you work in any sort of like large company, you'll notice that any pattern you introduce easily gets copied and reproduced at a very rapid rate. So once every developer starts doing this, you start to realize that you have something quite unmanageable, and it's actually really hard to undo and fix later on. So it's really important that when you introduce these building blocks into your code base, when you introduce something like GraphQL, that you're very conscious about what the implications of that implementation is. So let's see how we can improve this. The first thing we want to talk about is how can we even write a query? Like, what does a query mean? Like, well, how could we actually define and structure a query? Now, if we look at our initial request, we can see that repository takes a couple of arguments, and it asks for a couple of fields, and then it queries a relationship through owner, which is of type user, and it asks for that owner's avatar URL. So we could think about this more as there are some objects with arguments, there are some objects without arguments, and then if you sort of turn this on its side, at the leaves of this sort of tree, it's all fields. So we can actually now take our knowledge from earlier and create enums to model this. So we could create a model or create an enum called node, which has a couple of cases, and these represent any sort of section of that query. So in this case, a node can be either a field with a label, or it can be an object with a label and an optional list of arguments, and then a list of fields within it. And those fields are of type node. So it's the recursive case. So within an object, you can query any combination of other objects or fields. And the argument types is a tuple of string and input type, which just basically says what is the name of the argument and what is the type of it, so that we make sure that we actually capture the encoding information in our DSL itself. Now we can start to actually rewrite that raw string query with this as an instance of this enum. So we can have a label of repository, pass it the necessary arguments and a few fields. Then we can add owner and its avatar URL. And then we can add issues and pass the proper arguments and the title and state. And this is great because this allows us now to actually have a structured representation of what a GraphQL query is. It's a lot better and it's a lot more understandable, and we can build tools and code that actually describes this to us and actually performs optimizations on this. But now we just have a data structure, right? So we can write functions that know how to consume this data structure, like render a query string, which is what we're going to need to actually send to our API. So render query string is just going to take an instance of this node enum, and for a field, it's just going to return the label. For an object, it's going to return the label and then curly braces with a list of fields inside of it. And then for an object with arguments, it's going to have a label with the list of arguments and then the list of fields. And the list of arguments is actually rendered itself through a render argument function, which then just ensures that if we have an argument of type string, that it's quoted, and if we have an argument of type integer, that it's not. And this is great. It actually, at this point, we have something that we can actually use to write a GraphQL query, and it'll actually render to a valid query string. But we still have one problem. The problem is that we haven't actually provided any guarantees against the GraphQL query schema that we're actually working with. We could query relationships and objects that don't exist. We haven't brought that type system into our DSL. So I want to talk about types next. Now, with types, we're going to create an enum called query root. At the root of your GraphQL query, there's only certain objects you can start to query from. And in our example, this one's repository. So we're going to inline the arguments of owner and name, and then this last attribute, or this last argument, is a field selection on a repository field. And a field selection, as you can see type ls at the top, a field selection of t is just an anonymous function that returns an array of t. So in this case, the repository case, the last argument is going to take a closure that returns a list of repository fields. And what is a repository field? It's the list of fields and relationships on a repository. And we can do the same thing for user and issue. So you can see with repository, we have name, description, homepage URL. And then if you look at the owner case, it's a relationship because it has a field selection on a different enum type. So if you add a repository field of type owner, you have to also express a closure that says what fields of user you want for that owner. Now, we can start to rewrite our DSL like this, or we can start to rewrite our query like this. So now we actually have something that looks like the GraphQL query. We have something that takes arguments in the right type. We have something that enforces that we can't query fields that aren't in a repository. We can't query objects that don't have relationships to the object we're querying from. And this is great because now we actually have something that is quite concise. We have something that guarantees our schema relationships, and we're going to compile time errors, which is great because it brings that feedback loop of when you've made a mistake really early on in the development lifecycle. So, but we still have this problem now. We have a way to create GraphQL queries, and then we have another DSL for actually our fields and our field schema. So we need to actually bridge these together. And so what I found useful for actually bridging together things like this is just simply protocols. So what we need is we basically need to make our field DSL capable of producing nodes. So in this case, we'll create a protocol code called node renderer. It'll take one function called render node, which returns a node. Then we can make query root conform to render node. And you can see here that query root will just switch on itself, and it only has one case. So in this case, it's repository. And and its return will just return a node object with the proper label and arguments. And then if you notice the fields argument, we're actually going to map over that field selection, and for every field specified for that repository field, in repository field, it's going to render a node itself, which means that repository field has to conform to node renderer for this to compile. And so for all of our fields, we actually will add implementations of node renderer themselves. And the great thing now is that we're actually able to bridge the entire spectrum here. We're able to say that we have a field DSL that models our GraphQL schema types. Then we have a node DSL, which actually represents what our valid GraphQL query is. And then we're actually able to render that all the way to a query string that we can send to our API. So in this case, the query function is very simple. It just takes a field selection on query root. So basically, what can you query from the root of your GraphQL query? And then it evaluates that and turns those fields into nodes. Then it takes those nodes and turns them into query strings, and then it just joins them together. And to sort of illustrate this, I've put together a quick little playground for you. Can everybody see that? Is that a little small? I can bump that up. 1 second. There we go. So what I have here, I've taken everything we've talked about, and I've actually tossed it into a playground. So I have another file that's already compiled with all the types that we've talked about and all the DSLs we've talked about. So you can see that we're going to have a variable q here that resembles the result of this query, which in this case we have a repository that takes the owner Pinterest and Plank, and then it takes a name and description. And then below it, you can see that we have the actual output of what this query string is. So we can start to play around with this. And you can start to see it adapt. So we have the homepage URL, and then let's say we want to add the owner. And we want to add the owner's avatar URL. And this is going to keep getting truncated. And then what's actually interesting, outside of just seeing text input, is with playgrounds, we can actually have a simple live view. So I just whipped this up for us. So should probably make the text bigger, but what you can see is that for the query on the left side, we have the data we are requesting. So we can see what the avatar URL of the owner of this repository is. We can see the name, and we can see the description and the homepage URL. And then so you can imagine this experience for your developers where they have compile time safety. They can still move fast. They can actually develop queries within playgrounds. So you have things like this you can do now, where you can say for an issue, I want to get the title and state. And I have a compile error, so the compiler is saving me. I forgot to say how many issues. So let's say I get the first 10. And now you can see we have a list of issues on the repository I need to fix, and the name, description, homepage URL. But now that you have this in code, you have the full power of Swift at your disposal. So you can actually now do anything to sort of template this response. So you could say, let's say we had we create a function that represents our repository with issues query, and we're actually just going to return this here. And now we just need to take out the hard-coded stuff. And then we can update the call site. And it works. Well, maybe it's not working there. I don't know. Is that? Oh, there we go. And not only that, I mean, just to show you this isn't sort of a hard-coded response, I'm going to pick another speaker's stuff here. So John, sorry. John has a popular repository called Marathon, and I asked him last night at dinner if I could do this. So, but to his credit, it's hard to find an open issue on his repository, I found. I actually had to take it, I think, to 11, and then I found something. Oh man, maybe I took it to 20. I don't know. There was something about Zeesh, I think. But anyways, this is just sort of the start of what you can do with this. There's a lot of sort of rich features once you have this available in your code. You could add helpers for pagination. You could add further optimizations on your GraphQL query itself. And so you don't have to stop here at all. But let's see. So, but that's all I had. So I just wanted to say, Dziękuję. Is that Polish for thank you? Thank you. I'm Rahul Malik, and that's my GitHub. I have a repository called Writing DSLs on there, where you can actually get all the slides, and I have a playground. I have a playground with a few pages on it that goes through the various DSLs we've talked about, and you can grab it and throw in your own GitHub API token and play around with it. So thank you.